So this is Chapter 1, Section 4 on quadratic equations. And the first thing we're going to do is we're going to solve quadratic equations. Well, we're going to learn what a quadratic equation is, and then we're going to solve that equation by two methods. One is by factoring, which you should be at least somewhat familiar with, and the other is using the square root property. So let's first look at the general form of a quadratic equation. So it's a polynomial set to 0. Well, at least it can be converted to such. It's a degree 2 polynomial specifically. It has the form ax squared plus bx plus c, where a, b, and c are real numbers, but the leading coefficient is never 0. So that's how you're going to see them. You'll see them in many different forms. Just note that this is a quadratic equation here. Because it can be converted into the form ax squared plus bx is equal to 0, plus bx plus c rather, by just taking the 5 and moving it over. So in this case I have 7x squared plus 5 is equal to 0. You might be wondering where the bx is. Well, if b is equal to 0, then I can add 0 times x. So that's just kind of a trick. All of the terms are there. It's just one of the terms we don't write because its coefficient is 0. So let's look at the zero factor theorem. We use this all the time. So when we have real numbers, including complex numbers, if we have a times b equal to 0, then we can immediately know the following. Either a is 0, or b is 0, or both. So we're going to use that to solve this quadratic equation by using the zero factor theorem. So this is going to be example 1. So example, I'm just trying to get myself situated. If you're curious what I'm using this Wacom pad right here. I'm not using a touch screen device, and this is a little magnetic thing in the very end. But I have to orient myself just right so that the lines will work, and just bear with me if I start writing really slanted. So this is going to be example 1. I'm going to solve 6x squared plus 7x is equal to 3. So the first thing we're going to do is we're going to write this in the general form ax squared plus bx plus c is equal to 0. And in this case it's going to be pretty easy to convert to that form. I'm just going to move the 3 across the equal sign. Of course, the price we pay for that is the sign on the 3 changes from positive to negative. So this equation here and this equation here are equivalent equations. So now we're going to factor. And by now you should have a method of factorization that you like. If you've had my classes before, I teach this method. And if you've not and you want to know about this method, what I will actually do is post a video of it. This is my x term and this is my constant term. So basically what I do is I have to find what I do is I write my degree 2 term at the top, and then I skip, And at the very, very bottom, I write my degree 1 term, and then I put my constant term here. So what I have to do is I have to enter in numbers in this row and in this row that multiply to just the coefficient. That's all we're worried about. So, well, I mean, you can do it either way. I'll make it easy for you. I'll put 3x and 2x in here. And clearly 3x times 2x is equal to 6x squared. So now I have to choose numbers that multiply, they're whole numbers that multiply to give me minus 3. So the easiest choice, there's really only there's only two possibilities. I either minus 1 times 3 or 3 times minus 1. So now what do? Is I multiply downward. So the whole thing is filling out this box. Once you get the box filled out and the last criteria finished, you're good to go. So what I want to do is multiply down. So 3x times 3 gives me 9x. And 2x times minus 1 gives me minus 2x. And now we add. So this is multiplying. This is multiply, 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 multiply. But this last is add. And when I add them up, I have to get 7x. If I don't get 7x, then I have to change what's in the box. But in this case, 9x minus 2x gives me 7x. So now I can literally read off the factorization. And this is the factorization. You go kitty corner this way. So my factorization is 3x minus 1 times 2x plus 3. And that's equal to 0. Now I'm ready to use the zero product factor. I'm literally, for this is going to be the only time I factor that way. I will post a video that I use for my intermediate algebra. And if you want to know this method, you can review it. If not, factor however you know. But now I'm ready to use my zero factor theorem. Because if I call this factor A and this factor B, I have A times B is equal to 0. So by my zero factor theorem, that implies A is equal to 0, but A is equal to 3x minus 1, and that's equal to 0. And we have to look at both possibilities. And the other possibility is that B is equal to 0, but B is equal to 2x plus 3. So now all I have to do is solve these easy linear equations. So this is the same as 3x is equal to 1, which gives me x, divide both sides by 3, is equal to 1/3. Down here, this is the same as 2x is equal to minus 3. Then to divide both sides by 2, that gives me x is equal to minus 3/2. So our solution set, we have two solutions, and that's many times the case with quadratic equations, is two solutions. Never more than two solutions, but always at least one, because we're going to extend our number. We've extended our numbers to the complex, to include complex numbers. So our solution set contains this solution and this solution. So you just write them in there in any order. It doesn't matter if the negative comes first and the positive second, because sets are not ordered. They just contain elements in any order whatsoever. So that's our first example. So that's by factoring. Now we're actually going to do something else. I'm going to give you a theorem, and at the end of the lecture I'm going to challenge you to try to come up with its proof. And I'll give you a hint. It's pretty easy. So we're going to use this property all the time. If x squared is equal to k, then x is equal to the square root of k, or x is equal to minus the square root of k. So we're going to use that to solve each of the following quadratic equations. So this is going to be example 2. I have x squared is equal to 17. So literally, I'm going to write that implies x is equal to the square root of 17, or x is equal to minus the square root of 17. Now 17 is prime, so there's no way I can simplify the radical. So the solution set here would be minus the square root of 17 and the square root of 17. And the reason I'm writing this is I'm perfectly fine myself that you literally just write out in words. But my math lab may want you to write it as a solution set answer, in which case you would write this. So let's look at the second one. I guess this is 2b. So I have x squared is equal to minus 25. So that means x is equal to the square root of minus 25, or x is equal to minus the square root of minus 25. But here we have to use what we learned in our last lecture about complex numbers. This is equal to I times the square root of 25. But the square root of 25 is 5, so that's equal to 5i. And by a similar line of reasoning, we get the square root of minus the square root of minus 25 is minus 5i as well. So in this case, our solution set would have 5i and minus 5i. You might be curious, and I would be so pleased if some of you were asking, do complex numbers have a sense of negatives and positive? And the answer is no and yes. We have to create one, and it's not simple. So, but like I said, a set is just basically a set where you list elements, not elements in order. But the only thing I wanted to say is, in complex numbers, we don't have this relationship. Minus 5i is less than 5i. That's incorrect. That's not correct. So that sense of less than, equal to, greater than, or greater than or equal to doesn't extend to the complex numbers easily. I'll just leave it like that. And you'll never have to deal with them unless you are a grad student in mathematics. And then unless you're in analysis and complex analysis, you'll probably never even see attempts to try to extend the notion of less than, equal to, or greater than. Equal, of course, exists. But less than or greater than, that doesn't extend easily. So again, we have x minus 4 squared is equal to 12. So resist any temptation completely. What you do not want to do is expand x squared minus 4 and write x squared minus 8x plus 16 is equal to 12. Now, you'll get the answer that way, but you may not be able to get it with what you have yet. And it's so much easier to do it this way. We're just going to use the square root property, and it's literally sitting up here waiting for us to be used, which tells us that x minus 4 is equal to the square root of 12, or x minus 4 is equal to minus the square root of 12. Now clearly I'm going to have to do some simplifications here. I want to know how much x is equal to, not x minus 4. So I'm going to move the 4 to the other side, and it becomes plus 4. And do the same thing below. But now I need to simplify the radical. And just looking at the square root of 12, the square root of 12 is equal to the square root of 4 times 3. But 4 is a perfect square. 4 is equal to 2 squared times 2. So since the exponent is even, I can remove this factor from underneath the radical sign by dividing, since it's even, by dividing it by 2. So the exponent becomes 1. So that's 2 on the square root of 2. So my final preferred answer format is x is equal to 2. Sorry, that's a 3 there. 2 on the square root of 3 plus 4. X is equal to minus 2 on the square times the square root of 3 plus 4. Okay, so that's it for that one. Do I have anything below? Oh, we're ready to go to another objective. So now we're going to look at, get down there, solving quadratic equations by completing the square. So this is going to be something that is probably new to an awful lot of you, this concept of completing the square. Now what I didn't do in preparation is to show a quick video, a geometric video, that shows how this actually works. But you can always Google and say geometric proof of completing the square, and it's really kind of cool, and it's been used since ancient times. But let's actually look. A lot of what mathematicians will do are just look at examples and see patterns and then prove that those patterns actually continue to hold. I know several mathematicians or grad students in math who literally got into math because they like to see patterns, and numbers are full of patterns. So remember, a perfect square trinomial is one that can be written in this form, a monomial squared. So x squared plus 8x plus 16 is equal to x plus 4 squared. Okay, that's easy enough. You might want to review how we know that. X squared minus 6x plus 9 is equal to x minus 3 in parentheses squared. X squared plus 3x plus 9 fourths is equal to x plus 3 halves squared. So let's see if we can see the pattern. So in each case we have a monomial squared, so the x is the same in all three. What about the sign? Well, the sign in the monomial on the constant term is equivalent to the sign in the trinomial of the degree 1 term. So easy enough. But what about this term right here? The 4, the 3, and the 3 halves. Well, 4 is equal to 8 divided by 2. 3 is equal to 6 divided by 2. And 3 halves is equal to 3 divided by 2. So that's literally the pattern that leads us to this procedure, an algorithm if you want, on how to complete the square. So the first thing here is this only works if we have a monic degree 2 polynomial. And that's a word that your textbook doesn't use, which is unfortunate. A monic degree 2 polynomial, monic, is just another word that tells you that the leading coefficient on the degree 2 term is 1. So you don't have 2 here or 3 or anything else, you just have a lone x squared. That makes a polynomial monic. Its leading, its highest degree term has no coefficient other than 1. What's coefficient is 1. So given a monic degree 2 polynomial in the form x squared plus bx plus c, which is equal to 0, which is prime. So that means it can't be factored. That means we can't use our factorization methods to solve it. How do you know that? Literally the only way you can know at this point, and the only thing you'll ever learn in this class by looking at it, you just have to try it. It's trial and error. And if you do it in the right way and you use the right algorithm, you can literally exhaust every possibility, and when every possibility is exhausted, you can't go any further. You know it's prime. So that's kind of, you're really spending an awful lot of work to factor a polynomial if you don't know beforehand that it can be factored. So we're just assuming ours can't be factored, although it still works even if it can. So the first thing you want to do is you want to move the constant term. So which term is the constant term? It's the c term. You move it to the other side of the equation. So then you have x squared plus bx is equal to minus c. Now what we're going to do is we can't break the equality. So we look at our b term, which is the coefficient to the degree 1 term, just the x term, and we divide it by 2, and then we square it. And we add that to both sides of the equation. So here's an example of doing this. So I have x squared plus 2x minus 4 is equal to 0. So I'm going to move the minus 4 to the right-hand side. So that gets me to this step right here. And now the b term is 2. So I'm going to add 2 divided by 2 squared, which is equal to 1 squared, which is equal to 1. I'm going to add it to both sides. So when we do that, as it turns out, our left-hand side now magically becomes a perfect square trinomial that we can factor. How do we factor it? Well, we simply write x plus 1, and what is 1? It is our b divided by 2 term without being squared is equal to 5. So it's x plus b halves in parentheses squared. So clearly if b were negative, it would, or had a negative sign attached to it, it would be x plus x minus b halves squared. So let's just do one of these. It seems more complicated than it is, but it's really not, and this is definitely a skill you have to learn. Later on we're going to be looking, I don't know when, but it's in the future, we're going to be looking at circles and general equations for circles. Different circles and their intersections are used all the time. In what way? It's really quite fascinating. Suppose you're out on a hike and you have a bad asthma attack or some medical emergency occurs and you call for help. Well, you're out on a hike, you're not at your home address. And you can't tell them an address because you're out in nature. Well, the emergency responders can know where you're at by triangulation. And triangulation has to do with what we'll do later on. We look at different points and where the intersection of circles coincide. So, I mean, there's a lot of practical applications which are life-saving in math. And we're just building up to them right now by completing the square. So this is example 3. So I have x squared minus 4x minus 14 is equal to 0. So remember, the first thing you want to do is move the 14 to the other side. So my next step is going to be x squared minus 4x is equal to 14. So over here, what I normally do is I kind of make me some little notes over here. I know that my b is equal to minus 4x. My b halves, sorry, I got overzealous. My b term is just minus 4. There is no x there. My b halves is minus 4 divided by 2, which is equal to minus 2. And then finally, my b half value squared is equal to minus 2 squared, which is equal to 4. So what do I say do? The instructions tell us to add b halves squared, this value right here, to both sides of the equation. So that allows for the following simplification. X squared minus 4x plus 4 is equal to 18. And now the remaining perfect square factorization is just x. Remember, my middle term is negative. And here I just write this value in, which is, I've already written the negative down, minus 2 squared. So I have x minus 2 squared is equal to 18. And now we can solve it just using the perfect square, what was the name of that theorem? The square root property. So we get x minus 2 is equal to the square root of 18, or x minus 2 is equal to minus the square root of 18. So there's still a little bit of simplification to go on. Let me give myself, I have so much. This implies that x is equal to the square root of 18 plus 2. And this implies x is equal to minus the square root of 18 plus 2. But the question is, can I simplify the square root of 18? So we write down the square root of 18 is equal to 9 times 2. But 9 is equal to 3 squared, 3 times 3 times 2. So this becomes, so that's equal to 3 times the square root of 2. So this becomes x is equal to 3 on the square root of 2 plus 2, or x is equal to minus 3 on the square root of 2 plus 2. So my solution set is this. And the reason I'm doing this is some inner voice that may be wrong tells me that my math lab may at some point start asking for your solution set. Like I said, I may be wrong. So here is the next one. Did we do? Oh yeah, we just completed one square. So I only did one example for this. You should do several on your own. So our next objective is solving the quadratic equations by using the quadratic formula. That's what the book calls it. I often call it just the quadratic equation. And here is its derivation. So let ax squared plus bx plus c be equal to 0 be a quadratic equation where the leading coefficient a is greater than 0. If it's not greater than 0, just multiply through by minus 1, and it will be greater than 0, and you'll have an equivalent equation. Usually they give it to you that way. So what do? We literally symbolically complete the square. But we can't complete the square yet, because if we go back here, we have to have a monic degree 2 polynomial. This is not a monic degree 2 polynomial unless a is equal to 1. But we can make it equal to 1 by dividing everything through by a. So that makes our leading coefficient 1, and I have bx over a plus bc over a. 0 divided by a is still 0. Now what do? We take the constant term, we're completing the square. We take the constant term and we move it to the other side, and then we get this. Now what do? I find the coefficient on the x term, which is b divided by a, and I multiply it by 1/2 or divide by 2. They're the same thing. And I square it. So that's b divided by a times 1/2 is b divided by a, b divided by 2a, and then I square it. So this is all purely symbolic manipulation here. I get b squared over 4a squared. Then what do? I add that quantity, this quantity right here, to both sides of my equation. And now over here, my left-hand side is a perfect square. It is given by x plus just this part squared, b divided by 2a squared, is equal to b squared over 4a squared minus c over a. But the LCD of 4a squared and a is 4a squared. So we can change just the right-hand side to b squared plus 4ac over 4ac because I found the common denominator. So really all I'm doing is adding together these fractions. Now I'm going to use the square root property and take the square root of both sides. That gives me x plus b divided by 2a is equal to plus or minus b squared plus 4ac over 4a squared. We can pull out the 4a squared because that's a perfect square using the quotient rule and the fact that for the square root of 4a squared is plus or minus that. And that gives us, you don't care about this derivation, well I'm hoping some of you do because it's fascinating. It gives us the quadratic formula or the quadratic equation. So if you're given a quadratic equation, ax squared plus bx plus c is equal to 0, we have x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. That's it right there. I remember being in high school and I had a Hewlett-Packard calculator that used reverse Polish notation for input. It's a fascinating logical way to input numbers. It obviates, it makes unnecessary PIMDOS, and I could program it. And I programmed the quadratic equation in there just like that. I've had this memorized for such a long time. So here, listen people, you can use it even if a is negative. I think it's just easier to use the coefficient of the x squared term being positive. So if it were like minus 6x squared minus 4x plus 20, I would just multiply through both sides by minus 2. That means that you just flip the signs. You have an equivalent equation. But that's just personal preference. You can do it every way you want. So we're going to use and solve now, example 5, the quadratic equation, this quadratic equation by using the quadratic formula. So you might want to pause and see if you can do it on your own. If you don't have it memorized, you'll have to look at the quadratic formula. And I'm just going to tell you this right now. You should have it memorized. You're going to be taking your exams and working out how that's going to be done, and you'll be receiving some instructions on that sometime this week. It's always best to do things the way they would be done in the class. But if you have a formula sheet, this is what I know, people. If you have a formula sheet like this, stuck, these little sticky note things, stuck to your side of the computer monitor, I will never know. So that means those who cheat have an advantage over those who don't. And I don't like that. So that's all I'm going to say. You figure it out on your own, what I just told you. So here we go. Let's do number 5. So I have x squared minus 4x is equal to minus 2. But to use the quadratic formula, I have to have ax squared plus bx plus c is equal to 0. Remember, just because I'm writing plus here doesn't mean that b is positive, because b could be negative. And then plus or minus, I would normally write a b there. So let's just convert that to x squared minus 4x. Move the minus 2 over and it becomes plus 2, and I have that equal to 0. And our quadratic equation is that x is equal to plus or minus b, sorry, I wrote the plus or minus too soon. X is equal to minus b plus or minus the square root of b squared minus 4 times a times c. All of that is over 2a. So now it's just plug and chug after I've identified my a, b's, and c's. And that's what I always like to do. My a is the coefficient on the degree 2 term. So my a is 1. My b value is the coefficient of the degree 1 term, and it's minus 4. And my c is the constant term, and that's plus 2. So let's plug and chug, and we're going to have to do simplifications. And sometimes the simplification is where all of the work occurs. So I have x is equal to minus b, but notice b is already minus. So this minus b here, if b is already minus, I have to write b as minus. It doesn't get to co-opt that negative. That negative is independent. So this is minus a minus. Then I do plus or minus. b is minus 4, and it is squared. Minus 4 times a, which is 1, and c, which is 2. All of which is over 2 times my value of a, which is 1. So let's work on simplifying this. You can simplify it in many steps at once. For this first one, I'll just do it slow. Minus a minus 4 is 4, plus or minus. Minus 4 squared is 16. 4 times 1 is 4. 4 times 2 is 8, so 16 minus 8. Over 2. So that's going to give us 4 plus or minus the square root of 8 over 2. So let's work on the square root of 8. The square root of 8 is 4 times 2. So that's 2 on the square root of 2. Why? Because 4 is equal to 2 squared times 2. That's an even power, so I can move this term out from underneath the radical by dividing the exponent by 2. I feel like Spock here. Times the square root of 2. So this becomes 4 plus or minus 2 on the square root of 2, all of which is divided by 2. And in this case, you still need one more simplification. We use again a plus b divided by c is equal to a divided by c plus b divided by c. That's the rule we're using. So this is going to be 4 divided by 2 plus 2 on the square root of 2 over 2, or, so I'm taking the top value of the plus or minus, 4 divided by 2 minus 2 on the square root of 2 over 2. But yet there's one last simplification, and you will need to do it. 4 divided by 2 is 2. 2 divided by 2 is 1, so it's 2 plus the square root of 2, or 2 minus the square root of 2. So if I were listing these in a set, 2 minus the square root of 2, 2 plus the square root of 2. If this were a paper test, I would be absolutely all right with the following: 2 plus or minus the square root of 2. So you'll have to do it. Our tests are going to be given to you in MATLAB. That's a high probability. I've got to think really hard today, and that's one of the reasons I'm doing this is you'll be required to enter answers in MATLAB and write your work out and submit it too. So it's good to know how my MATLAB wants them done. Here's another example. And you all probably know that better than me because I'm not doing the MyMathLab homework in MyMathLab. I will work out problems that you send to me and sometimes look over a few challenging problems and present them to you, but normally we don't have time to do the latter, and if they're challenging, most of you don't want to see them anyway because those would be given as a bonus. So let's go ahead and solve this one using the quadratic formula. 2x squared is equal to x minus 4. So I have to get it into the form that I can use. So everything has to be on one side and 0 on the other. So x moves over and becomes minus x. 4 moves over and becomes 4. And we're going to solve this using the quadratic formula. So my a value is 2. So ax squared plus bx plus c is equal to 0. My b value is, that's the same as minus 1 times x. And my c value is 4. So I have x is equal to minus b plus or minus the square root of b squared minus 4 times ac over 2a. So that's equal to minus 1, because b is minus, plus or minus the square root of, b is minus 1 squared minus 4. My a is 2. And my c is 4. Give myself some room here. All of this is going to be over 2 times 4, because my a is 4. It's right there. So let's go about simplifying. So that's equal to minus a minus 1 is 1, plus or minus square root. Minus 1 squared is 1. 4 times 2 times 4. That's 8 times 4. That's minus 32. All over 8. So, simplify again. That's 1 plus or minus the square root of minus 31 over 8. But it's okay. We just discovered that my answer here is a complex number. So that's what x is equal to. So here, this is 1 plus or minus the square root of minus 31 is I times the square root of 31 over 8. And I'm okay if you leave it in this form. However, just to be correct, since this is a complex number, you want it in the form a plus bi. So that means it's 1 plus I over the square root of 31. 31 is prime, so it can't be, there's no simplification to that radical, over 8, which is equal to 1/8 plus square root of 31 over 8 times I. Or it's equal to 1 minus I on the square root of 31 over 8, which is the same thing as 1/8 minus the square root of 31 over 8 times I. That's writing it in the form of a plus bi. Okay, what's our last thing? Oh, we're going to solve quadratic equations completely in general, but it's not too hard. We're solving formulas. We're solving for a quadratic variable given in a formula. So going back to what we're given, we're going to solve both of these equations for the specified variable. And I give you the hint, don't forget to use plus or minus when taking square roots. And depending on what's actually being solved for, you might want to only use one or the other. For example, this is the area of 4d squared divided by 4. This is an area formula. I want to say it's the area of a sphere, and the area is always positive, so you'd only take the positive value, but we're not worried about that right now, because I've not told you what a is equal to pi d squared over 4 stands for, and it may be it's some formula where a negative answer does make sense. So let's do that. Which one is this? This is 7. That's example 8. So this is example 8. I have a is equal to pi times d squared divided by 4. And I'm solving for d. So what do? We have to isolate the d term. So this has a fraction in it, so the first thing we do is we multiply both sides by, there's only one fraction, so we multiply both sides by the denominator, which is 4. And that clears the denominator, because I have to maintain the equality, I have to multiply both sides by the same number. And 4, when I multiply this over here by 4, and this by 4, this is the same as 4 divided by 4 times pi d squared. So that just gives me pi times d squared. So pi is a mathematical constant. So pi is approximately equal to 3.1415926, and it goes on and on. We don't care. We just keep pi. We want an exact answer. So we just pretend like pi is a variable. So what we need to do is I have to isolate the variable I'm solving for. So it means I have to divide through both sides by pi. So that gives me 4a divided by pi is equal to d squared, or d squared is equal to 4a divided by pi. So now I just use the square root property. I take the square root of both sides. So d is equal to plus or minus the square root of everything, 4a over pi. This has a simplification. Using this implies that a, that's supposed to be a double arrow. Double arrow in math means implies. There. So this implies d is equal to plus or minus. Now I'm going to use a quotient rule for fractions. The square root of 4a divided by the square root of pi. So that has one further simplification. Since 4 is a perfect square, 4 is 2 times 2, I can move it out from underneath the radical. So 2 on the square root of a divided by the square root of pi. And if you go any further than this, it's purely a matter of taste. That's what d is equal to. I'm quite fine, you stop right there. But you might also see it, d is equal to plus or minus 2. Again, reversing the rule of radicals that I just used, a divided by pi. These are equivalent answers. And to say that one is better than the other is introducing subjectivity in tastes. It depends on the application. If you're a computer programmer, it's probably it could be easier to deal with a divided by pi, but probably not. This one's probably going to be easier. It just depends on the application, and that's all I'm going to say. So they're both equivalent. I don't care. My math lab might. I don't. So finally, we are on B. I guess this is 8B. So R t squared minus st is equal to k, and you're freaking out. Don't. We're going to solve for t. So the first thing I'm going to do is, if you've wanted, literally, if it makes it easier for you, change the t to an x. So I'm going to have r t squared. I'm going to make it into a quadratic equation in the variable t. I'm just sensing some freaking out right now. So a t squared minus b t so that's one step away from the general a x squared plus bx plus c is equal to 0. So you're familiar with that. So literally all I did to get from something you're familiar with to something you're not is I replaced the variable x with another letter, t. And then what did I do here? My coefficients are themselves variables. So my a is equal to r. My b is equal to minus s. And my c is equal to minus k. So now I'm ready to use what? I only have one choice here. It's the quadratic equation. But then I don't have to worry about simplifying it. So I go x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So what do I do? My variable, this is an equation in the variable t. So this gives me t is equal to, what is minus, and what is b? Minus s plus or minus the square root of, what is my b? It's my minus s minus 4. And what's my a? My a is r. And what's my c? It's minus k. All over 2 times a, which is r. So the simplification is going to be minimal. But we can simplify. So the final result is going to be t. Minus a minus is plus. I can drop that. So that's a s. Minus s squared is the same as s squared, always. Minus 4 times r times minus k is minus times minus. Minus times minus is 4 times r times k. And it's all going to be over 2r. And that's it. You can't go any further. But that is the solution right there. T is equal to s plus or minus the square root of s squared plus 4rk, all of that's underneath the radical, over 2r. Okay. Seems like I might be skipping something, am I? Nope. We're ready for the last thing. So the last objective is the following: determining the number and type of solutions by the discriminant. So what is the discriminant? Well, let's take a look. So the discriminant, here we have the quadratic equation. And in blue, I have written the discriminant. And as you know, if b squared minus 4ac is less than 0, the answer is going to be a complex number. So that helps us understand, by using the discriminant, where the solutions lie, what type of solutions they're going to be, etc. So notice that this is the discriminant right here. B squared minus 4ac. Not its square root, just b squared minus 4ac. So as it turns out, if, this is important, if a, b, and c are integers, so they have to be integers, those are plus or minus whole numbers, like minus 3 plus 127, 0. If a, b, and c are integers, then you can use this test. Knowing information about this discriminant tells us information about the number and types of solutions we get. So if the discriminant is positive and its square root is a whole number, for example, if the discriminant were 25, then the square root of 25 is 5. That means 25 is a perfect square. Then we're going to have two solutions that are rational numbers. If it is, the discriminant is not a perfect square, then we have two solutions which are irrational numbers. If the discriminant is 0, then we have one solution, and it's called a double root, and it's rational. And if it's negative, the discriminant, remember the discriminant is b squared minus 4ac, then we have an irrational a complex number solution we have a complex solution a plus bi, where b is not equal to 0. So it's a full-on complex number. So let's try that with these three. So it won't be hard. Knowing the discriminant is really important in the history of math. There's a whole subset of math that just examines discriminants. Of course, discriminants come out in different types in different mathematical structures. In linear algebra, given a matrix that is square, you can compute the discriminant. So let's identify my a. So this is ax squared plus bx plus c is equal to 0. So my a value is equal to 5. My b value is equal to 2. And my c value is equal to minus 4. We have to take the minus. So the discriminant is b squared minus 4ac. So let's figure out what that is. B squared is 2 squared minus 4 times 5 times minus 4. So b squared is 4, and minus 4 times 5 is minus 20, times minus 4 is plus 80. So the discriminant is 84. So 84 is not a perfect square. It's close to 1. 81 is a perfect square. 9 times 9 is 81. But then the next perfect square is 10 times 10, which is 100. So it's positive, but not a perfect square. So by my list, we have 2 rational solutions. So I'm just going to start you out on the next one, and I want you to do the final 2. The answers are in the book, so you can check your answers. But let's do at least number B. Start it out. I'm not going to finish it. Let's find out using this discriminant. So first of all, in each one of these cases, our coefficients are integers, so we can use the test. If this were 5 halves or 4/3, we couldn't use this test. So let's do number 9b. So again, x squared minus 10x is equal to minus 25. We have to put it into standard form, x squared minus 10x plus 25 is equal to 0. My a value is the coefficient of the x squared term. My b value is the coefficient of the x term. And my c value is the constant term. So now what we have to figure out is the value of b squared minus 4 times a times c. In other words, minus 10 squared minus 4 times 1 times 25. Oh, it's easy, right? So this is 100 minus 100. So the discriminant is 0. So we have a double root. We only have one solution, and they're real numbers. Now I'll let you do C on your own. Let's look at this last mathematical reasoning. So I ask you to algebraically derive the square root property given on page 1 by starting with the statement that x squared is equal to k, and using algebra and properties theorems given in this worksheet to show that x is equal to the square root of k, or x is equal to minus the square root of k. And here's the hint. The hint literally tells you everything you need to do. Write k is the square root of k squared, and use the difference of square factorization. And once you do that, you're done. Okay, that's it for section 1.4. If you have questions, hit me up on Teams or just shoot me an email.